Okay, last time we talked about WKB. Today, we're gonna do see multiple scale analysis, or we also may know it as 2 times perturbation period. So the basic technique is that we distinguish between t and tau. These are 2 time scales. We call t fast time scale, and tau is usually is like epsilon times t. So this is slow time scale, and we find our solution as a function of 2 variables, t and tau. So as usual, we expand it using this series epsilon. Yeah, and in most cases we use 2 times perturbation period, and we have resonance terms, and we call it secular terms. For example, if in the solution you have this term or this term, we call them secular terms, and actually in real physical solution there is no such terms. So that's why we need to use this 2 times perturbation period to eliminate these secular terms. Okay, so let's solve this example. Y double prime plus y equals epsilon times y prime minus 1/3 y prime cube. So we need to use multiple scale analysis to determine the stability of oscillations. Yeah. So as usual, we start with this expansion. So our solution is y naught tau plus epsilon y1 p tau, and now we plug in this solution to the original equation. Yeah, and we also have to be careful with the derivatives. So now, because we have 2 variables, we need to define derivative with respect to t differently. So our derivative with respect to t is partial derivative with respect to t plus epsilon times partial derivative with respect to tau. Okay, therefore the second derivative is just square of this. So it's plus 2 epsilon times t tau plus epsilon squared t tau squared. And again, the main idea of this method is the following: that we treat these 2, t and tau, as independent variables. So even though you can see that they have the certain relationship, we treat them as two independent variables. That's why this term, so it doesn't matter to how to take the derivative. First with respect to tau and then respect to t, or vice versa, because they are two independent. Okay, now then we know how to compute the derivatives. Let's rewrite this equation and plug in this expansion. So we have, and for shortcut notation, I'll use dt and tau as this. It's the same. Okay. So here we have d e squared plus 2 epsilon dt d tau plus epsilon squared d tau squared. This operator acts on this expansion. Y naught plus epsilon times y1. Here this is the first term, then plus y naught plus epsilon y1. And the right hand side is epsilon times dt plus epsilon d tau times y naught plus epsilon y1, a minus 1/3 dt plus epsilon d tau times y naught plus epsilon y1, and all of this cubed. Now I need to write the same equation for epsilon in the power of 0 and for epsilon in power of 1. So let's collect the terms. Here we have second derivative of y naught with respect to t plus y naught and that's it. Here all the terms
minus dt y naught.
it's inside the parentheses, so
Okay.
yeah, it's here. Epsilon times
It's
1/3.
One more.
So it's like one line, all of this. So that's why the sum equals 0. Okay? And we know the solution is just the harmonic oscillator equation, right? For the frequency of 1, and y naught is a times e to the power it plus b e to the minus it. But we know that y naught and y1 is a function of y naught is a function of t and tau. So the exponent is a function of t, and therefore these two constants, they are a function of tau. So you can imagine it as, for example, you have a wave packet, for example, and your exponent, it's like a frequency of this wave. But this constant they are like envelope of this wave packet. So an envelope has a much smaller frequency. This is the frequency of envelope. So it changes slowly, while this wave itself, it oscillates much faster than the envelope. So that's why we can write here that A and B, they are functions of tau. But we want that our solution has to be not complex but real. If it's real, then so if a number is a real number, its complex conjugate should be equal to the number itself, right? So therefore, if you want to this solution be real, you need to say that complex conjugate of this equals to this, right? So complex conjugate is A star times tau e to the minus I t plus B star of tau times e to the IT. Okay, so complex conjugate equals to function itself. So what do we see here? We see that this has to be the same as this. So A tau has to be equal to D star of tau, right? And A star should be equal to B. So that's why basically we can use only one constant when we write the solution. So we can write the same solution in this form. So instead of some other constant d, we'll use complex conjugate of the constant a, because the solution has to be real. Okay. This is function y naught. But to eliminate these secular terms, we need to calculate the next order correction.
Where we see the particular terms here?
Here we don't see them. We only see them in the next term corrections.
Oh.
So and okay, let's see. For y1. We have secular terms only in the case then we have some right hand side which is non-zero. You have, for example, here some force that has the same frequency as this part. So if you have your term like sine of t or cosine of t, eventually will have resonance, and in the end, these terms. But because here we have zero, so in the zero folder, nothing special, just regular harmonic oscillator. So what happened when we collect terms of epsilon? So we have 2 times dt d tau y naught. When we have plus d squared t by 1. That's it here. Then plus by 1. And equals to d y naught, right? And here we have d cube, dt cube,
Yes.
and y naught cube.
Why not you?
And that's it. All of the other terms, they will have power greater than 1
Yeah.
for epsilon.
So you have also the 3 y naught squared epsilon y1.
Yeah, but it will be epsilon squared because
Ah,
I have
because
one
you have
epsilon.
epsilon of okay,
Yeah.
okay.
So that's why just minus 1/3 d
Why not?
y naught cubed. Okay. So d squared t y1 plus y1 equals to minus 2 dt d tau y naught minus plus dt y naught minus 1/3 d y naught cubed. But in this case, we will have resonant terms because we have non-zero right hand side. And now let's calculate actually the all of the derivatives and we'll see. So the only terms that will be resonant, they are with like sine of t, a sine of t, or because we're using not sine and cosine, but epsilon for complex notation. They like this. With frequency of 1, because this solution of homogeneous equation has this point. Because if this part is 0, homogeneous equation, the solution is the same as in the previous order, right? So that's why we have to pick constant, not constant, this a function such a way that it will eliminate these terms. Okay. Right. So dt y naught. So we use this y naught. Again, tau is independent variable. So when we take derivative with respect to t, so tau is just constant. So we have I times a e to the it minus I a star e to the minus it. Okay. The next one, d tau t. Okay, I need to take derivative with respect to tau from of this. So it's I a prime e to the it minus I a star prime to the minus n. Now let's plug in. So we have minus 2 times I a prime e to the it minus a star prime e to the minus it. That's this cross term. Then plus derivative plus I times a e to the it minus a star e to the minus it. And the last one is this cubic term. So minus 3/2. And I need to calculate the cube of this. So basically I can write this like I times all of this and calculate cube of this and cube of this. Cube of I is minus I, so therefore I have here plus and times cube of this. So a cube times e bit. Okay, then I have plus 3 minus 3a per a star times e to the it, and plus 3 times a star where, and here I have e to the minus 18. And the last one is minus a star cube times e to the minus 3it. Okay, now we need to track only terms that has power it or minus it. So because the equation will be just complex conjugate, we can pick only these terms or these terms. So if we eliminate one of them, the other one will be also here. So let's pick this term with plus sign. We have here one, and here one. Okay. And we want them to be 0. So let's write it down. So we have minus 2i a prime, then plus a I minus, you have I over 3, and here we have 3, so total is just I times a square a star 1 to the equals 0. So we have this differential equation. So it's minus 2 prime plus a minus r equal to. And this I can rewrite as a cubed. So I need to solve this, and usually I can write a in form tau amplitude times e to the I delta tau. In this way. So the derivative of it is just, so I have minus 2 times e delta prime times a. Okay, let's explicitly. This is the derivative of this one. But then I have like this. So of the exponent times r of tau, then plus r prime tau, all of this multiplied by e to the I delta of tau. Yeah, that's how I calculate the derivative of this. Okay, but then I have also this and this. So it's plus r of tau times e I delta of tau. And this one is minus r cubed of tau e to the I delta of tau. Now I can divide both sides by the I delta. And I have imaginary part of this equation and real part of this equation. So in the imaginary part I have only this term.
Due to the last term,
This one.
yes, it's supposed to be e with a 3 I theta.
No, because here I have a squared, so it's 2 I theta, and from this conjugate minus,
Yeah.
so that's why everything's
So-
fine. Yeah. So for imaginary part, I have theta prime times r equals 0, and for real part, I have r prime equals to r squared, just r times 1 minus minus 1.
So you have a minus outside.
Yeah.
Or minus 2.
Minus, yeah, I forgot about the minus 2. So here minus 2. Okay, then r prime is 1/2 r 1 minus r squared. Okay. Okay, what is the solution of this one? So the non-trivial solution is beta equals constant, right? I mean, we can use r equals 0, but it's a trivial solution for A. Therefore, for the whole equation. So that's why non-trivial solution is beta equals constant. Okay, and let's have a look at this equation. So we need to analyze the stability of oscillations. You see here that there are 3 points: r equals 0, r equals plus minus 1. These are the stability points of these oscillations, meaning that if r is equal to 0, you see that it will not change, right? Because the derivative of this will be 0. The same is here. If r is exactly plus or minus 1, nothing changes. But what happens if we step away from 1 or minus 1? Let's analyze.
It becomes dampening.
So if we start with r equals 10, what will happen?
There's a dampening force.
The right hand side is negative, right?
Yes.
Therefore, the derivative is negative, meaning that r is decreasing. And it will decrease until 1. Yeah. And then it stabilizes. And will be always plus 1. So if r is 0.01, we have like inverse picture. Right hand side is positive, meaning that derivative of r positive, and r is increasing again until it reached the value of r equals 1. Then right hand side is 0 and everything is stable. Okay? We call it limit cycles. Okay, questions? So it always goes to 1 or minus 1.
Also at 0?
If it's 0, it's
Yeah. 0.
Yeah. I mean, if for non-trivial,
Around 1, it goes to 1.
yeah. So whenever you start between, if you between 0 and 1, you end at point 1, or if r is, I don't know, 1 million, after some time again,
Goes to 1.
that's the idea. Okay. So in the next example, y double prime plus omega square of epsilon times t y equals 0.
We don't need to continue to solve this.
Oh, I mean, we can, but we have to know what is the boundary conditions, but we don't know. And the point of the problem was just to determine the stability points and analyze this limit cycles and oscillations. Yeah. So in the next one, we have linear oscillator with frequency that slowly varies. Okay, and we need to show that this actually this multiple scale analysis of this equation recovers the WKB optical. That's the idea. So again, we the solution is y naught t times tau plus epsilon y1 t tau. Okay, and let's rewrite this equation. So dt squared plus 2 epsilon dt d tau. I don't need to keep higher order terms higher than epsilon. So that's why I neglect the term of epsilon squared times y naught plus epsilon y1 is 1, okay, and plus omega square of epsilon t times y naught plus epsilon y1 equals 0. So for the epsilon of the Fourier order, we have e square e y naught plus omega square epsilon t y naught equals 0.
The omega squared is a function of the epsilon t. Okay.
Yeah. It's a function of
It's a function of
changes slowly. Okay. So you may think that best option to write the solution is this, right? So t times t, here we have omega of tau t plus a star of tau e to the minus I omega of tau times t. But in this case, it is wrong. Why? So if we calculate the first derivative of y naught, okay, for example, we will have this term. With respect to t. Okay. So let's take this one. So it's a of tau times the derivative with respect to t of this. What is it? Is the exponent itself times the derivative with respect to t of this. So, and when we calculate the derivative, here we will have two terms, right? One with
why you have two terms? You have just
no. I mean, okay. So I mean this derivative.
Okay.
So that's yeah. So with this derivative will be proportional to, so it will be like omega prime respect to tau times t, and plus other terms.
Mhm.
So because it has the secular term, the derivative of y naught, we can't use this form. So we actually mix with the slow time scale with the fast time scale. Okay, we want to keep slow time scale only in this amplitudes, this prefactorial exponent. So that's why the best way how to write the solution of this one is to use not omega but phase. So in terms of physics, we'll use not angular velocity but the phase. The phase is something which can oscillate fast. So our psi is basically integral over omega d d. Or we can rewrite it as omega. So because t tau is epsilon t, so t is tau over epsilon. So here's my tau, the tau, and 1 over epsilon, I can write it outside of the integral. So I integrate over tau. Okay? So that's how I define psi of t. And the proper solution is with this phase. So y naught is a of tau times e to the I psi of t times t plus a prime of tau e to the I minus I psi t times t. This is proper one. And because the derivative of it will not mix the terms, we will use this one. Okay. Now we need to write the next term, right? The next order approximation. So what will I have for the next order approximation? Basically, I'll have this term, right?
You split even one
Yeah.
one.
Yeah. So we need to compute the derivative of our y naught solution, right? And then plug it in into the next order equation. So let's calculate y naught prime. So, and again, by prime I mean this operator. Okay, is just the derivative with respect to. I think I write it Yeah. Of y naught. So we use this one, okay, and we'll have a times d I. So times the exponent. This is the first one. Then I have plus epsilon times the derivative with respect to tau. So it's a prime times the exponent. And plus complex conjugate of all this. Complex conjugate came from this second term. Okay. So then I substitute all of this into second order equation. And yeah, I'll have this epsilon times 2I omega times a prime plus I times omega prime. Okay. So this is my resonance term, and I want to be this equal to. So this is the next order correction. And what do I have? I have 2 a prime equals minus omega prime a omega cube. So basically it's 2a prime over a equals minus omega prime over omega. Okay. Now the solution is a tau equals the constant over the root of omega. Okay. This is amplitude. And now the final solution is this amplitude times this exponent plus the same complex conjugate. So basically, our solution is c over omega epsilon t times the exponent, and in the exponent we have e over epsilon integral of omega tau to tau. And plus complex conjugate. And you can recognize the WKB. So basically that WKB has the same approximation. You have the first term of WKB is 1 over epsilon s naught plus 1s plus epsilon s2. So this gives us first term. Okay. So, and the last problem is we will solve boundary layer problem, but we will show that we can basically use multiple scale analysis to produce the same answer that boundary layer theory gives us. So we have usual boundary layer problem, epsilon y double prime times a times y prime plus b times y equals 0. We have boundary conditions. I have notice a of 1 is b, and a and b, they are positive constants. So we know that using boundary layer technique, we split the domain into inner and outer solutions, right? And then match them. So can you guess how we can solve this problem with multiple scale analysis? Pretty much the same thing. What will be our inner and outer variables? Now remember, outer solution was like smooth, slowly varying solution, while inner solution was like the solution that changes fastly.
The tau is the outer and the
Yeah, exactly. So tau, it's like our time for outer region, and t is the time scale for the inner solutions. So that's why we just simply rewrite the derivative with respect to x as then dt plus epsilon theta. And we'll show that this gives us the same thing as we got before. Okay. So t our inner solution how outer. So, yeah, let's write it epsilon. Then we apply second derivative. So second derivative is d squared dx squared is d squared t plus 2 epsilon d tau plus epsilon squared t tau squared. So we apply this to y, and y again is a function of two variables. So it's like 1 over second. Yeah, so we need to let's mesh it properly. So our t is like 1 over x, okay? So it's like, remember that we have the same for inner variable. We call it x tilde. Right? But here we call it t, so time scale. And yeah, that's why the proper equation for this derivative with respect to x is 1 over epsilon. You have just the tau, because tau is epsilon times t. So meaning that if you multiply here by epsilon, you have epsilon t, which is tau, and the derivative is, yeah, it's the same. But when you differentiate with respect to t, you have to adjust this factor. So that's why, let me try to carefully. So the second derivative will be 1 over epsilon squared, then plus 2 over epsilon d dt tau plus d tau squared.
And over epsilon squared t squared. Just one.
Yeah. Thanks. Yeah. So now epsilon times the second derivative, so it's like 1 over epsilon squared dt squared times times y naught plus epsilon y1. Okay, I plug in the expansion for epsilon, which is the same, plus 2 over epsilon dt d tau of y naught plus epsilon y1. Okay, and then plus the tau square of y naught plus epsilon y1. Okay, that's it for the first term. Then for the second term, is plus a times 1 over epsilon d t of y naught plus epsilon y1, and then plus d tau of y naught plus epsilon y1. That's the second term, and the last term is plus b times y naught plus epsilon y1. So now let's keep track of the leading order. If we multiply all of this by epsilon, okay, so we'll have here epsilon squared, here we'll have epsilon, here we will have epsilon. So the leading order is about epsilon, so I take this term, right, d over t of y naught, and then here I have from this term that's it. This term is a times this, right, plus d t y naught, and the third term is higher. So okay, I know how to solve this. This is just y naught is equal to t1, t1 plus t2 e to the. Let's be careful because here I have a, so that's why I should write here a. the constant, right? So yeah, minus square root of a times d. This is basically the solution of the equation. Sorry, just a. Okay.
Minus or
Minus, yeah. And because I'm looking for the expansion of y as a function of t and tau, I need to assume that this C1 and C2 they are functions of tau, as we did before. Okay, so this is function of tau and this is function of tau. Okay, now let's do higher order to define these functions. Order of epsilon. So for order of epsilon, I have here y1 d squared. Here I have this term, cross term, order of epsilon plus 2 dt d tau of y naught. Okay. These high terms from this one,
first one.
what do I have?
The first one, a dt y not.
I'm looking for
First order,
epsilon.
first order, yeah.
So it's
Second
this one.
y1, yeah.
So plus again a times dt of y1, and from this, actually, we have
No.
plus d tau, yeah. So plus a times d tau and d tau of y naught, and from the last term, b times y naught. So plus b times y naught equals 0. Okay, so now I have again the same equation for y1, but I have some terms that I put to the right hand side, and I need to be sure that there is no resonance with these two terms. So I have dt square y1 plus a times d tau y1 equals 2, and the rest I'll put to the right hand side. So minus 2 dt d tau y naught minus a d tau y naught and minus by naught. Okay, so in this case, what are the resonant terms that I'm looking for?
With AT?
Yeah, this one and
constants.
with constant, right? So I need to track that. So let's calculate the derivatives. So this is my, let me put it in the red box, my solution, and I need to find the derivatives, right? So d tau of y naught. So d tau of y naught is just c1 prime plus c2 prime times e to the minus at. Okay, this is this term. Then the cross term, right? d of d tau y naught. So I need to calculate the derivative with respect to t. This term derivative 0. This term minus a t2 prime e to the minus at. That's the derivative. Okay, now we can plug in all of this into the right hand side and see what are the conditions for C1 and C2. So minus 2 times this, so it's plus actually, plus 2 a c2 prime e to the minus 18, and then minus a times c1 prime minus a c2 prime a minus 18 and minus e times the solution.
The E, no, not A.
Oh, that's it. E, thank you. And b times c1 minus b times c2 e to the minus 8.
What the terms are not.
Yeah, we need to fix it. So let's pick the resonant terms. They are resonant for this, right?
Mhm.
They are constant. And this, and this, they are resonant for this solution. The second one with the exponent. Okay, so now we need to,
Zero.
yeah. So we'll have two equations. The first one for one resonant term, the second one for
Leave him here.
okay. So the first one is minus AC1 prime minus B1 equals 0. We can solve it, right? So
C1 prime with respect to tau, yeah?
yeah, C1 and C2, they are functions of tau.
Okay.
Yeah. So we have C1 prime over C1 equals minus B over A. So and therefore C1 is some constant times E to the minus B over A times tau. So let's call it K1. Okay. So now for C2. For C2 we have more terms. Let's write here. So for C2, 2 AC2 prime minus. Okay, so because
Oh, please be.
all of this, the sum of these three should be 0. That's why I can cancel out the exponent. Yeah, and
The same.
so I
solution.
have just this equals B times C. You see? Here I have 2A times C2 prime minus AC2 prime.
C prime here.
Yeah.
Okay.
Okay. So, and then C2 is some K2 e to the B over A with a plus sign. Times tau. Okay. And now to find what are the K1 and K2, I need to use the boundary condition. Exactly. So now I can write the solution. Here is my solution. So it's C1. C1 is K1 e to the minus B for A tau times what's it plus K2 e to the BA times tau times e to the minus 18. Okay, at x equals 0. So basically, x equals 0 is my inner region. right?
Yeah.
So it's then
Tau equals 0.
has to be all of the variables. Yeah, and x equals 0. Have basically my solution is k1 plus k2. So at this point, tau and t is 0. Okay, that's my first equation, and has to be a. And then x1. Now basically I'm working in the outer region, right? In the outer region, I have k1 e to the. So my solution is. So the point is, then I go back to the.
When you say when x equals 0,
Yeah.
tau equals 0, it's okay.
And,
Why?
and t is also equal to 0. So when I go back from this
Not equal
to the boundary conditions,
Mhm.
I treat this as not two independent variables, but as they depend both on x. So that's why then it's 0. I mean, t and tau 0. Then x is 1. So I write it as k1 e to the minus b over a plus k2 e to the b over a times e minus a over epsilon. Also. So I go back, so I define t as x over epsilon. So then x equals 1, t is 1 over epsilon. Okay? And tau is just 1.
Okay.
So now we need to find k1 and k2.
Never end.
Hmm?
It's never end.
Almost there. So look at this term. That epsilon goes to 0. This term goes to 0, right? Because this goes to minus infinity and exponent goes to 0. So that's why we can simplify this equation and write that k1 is d times e to the b over a. So this is just 0. Okay. And then we know, if we know k1, we can plug in k2. K2 is a minus k1. So a minus b, a b over a. Okay. So, and the final solution is this. Okay. And basically, the form of the solution is the same if we did it with the boundary layer theorem. So if we do boundary layer theorem with the same procedure as we did before, and in the end sum up inner solution and outer solution and subtract matching solution, we will have the same answer. Okay, so that's why.
Where is the 1 minus x come from?
Then you multiply the terms.
Okay.
Okay, so that's it for today.
Can I ask you just one question?
Yeah.
For the homework. I asked you for the extension.
Yeah,
It's me.
yeah. I saw your photo in the WhatsApp.
I almost finished, but I found that it's very complex. The hardest one.